Here's a kinematics question which makes use of quite a bit of calculus to be able to solve it. So let's read the question, but first it's probably worth noting that this is the kind of question that you might see as a first year undergraduate student, right? Even if it's just kinematics, it's not very likely that you will get this in high school because usually around the time you do kinematics in high school, you don't really learn calculus. But let's read the question and let's try to understand what we have to do. So a test projectile is fired horizontally into a viscous liquid with the velocity v0. So we have this right here. We have the projectile going into the tank initially with the velocity v0. And then we have this acceleration, or rather deceleration, which is given as minus kv squared. And then we have to derive expressions for the distance traveled in the liquid and the time required to reduce the velocity to half of its original value. And then we can neglect any vertical motion. So the bullet doesn't actually move up or down. So let's try to understand what's actually happening here. We have at an arbitrary position in this liquid, I'm going to draw the bullet like this, and let's try doing this a bit better. So this is going to be my bullet, and at this particular moment, the bullet is going to have a velocity v, and it will have a deceleration, which is opposite to the direction of velocity, right? And this is a, which is proportional to the velocity squared. So this is what we're going to use as our starting point to find out expressions for distance as well as for time eventually. So here's what we can write. We've got that a is equal to minus kv squared. Now let's try to decide the order in which we're going to solve this. So the question says derive expressions for the distance traveled, which is one thing, and then the other thing is find the corresponding time to reduce the velocity to half. So the first thing I'll do is I'll try to answer the first question by finding the distance. So to do that, I will express acceleration in terms of, the first derivative of velocity. So a is dv over dt, which is minus kv squared. And straight away, we can actually find what the velocity is by solving this differential equation. But what I'll do instead is I will eliminate time, and then I will use that to find the distance in terms of the velocity. So here's what we can use in that regard. So we know that acceleration is dv by dt, and we also know that velocity is dx by dt. So using those two, we can actually write acceleration as dv by, and then instead of dt, I'll just write dx over v. So acceleration is just v dv over dx. And in this way, we get rid of time. So we have that v dv over dx, which was, remember, this is the acceleration. This is equal to minus kv squared. And one thing we can do straight away is we can cancel out one velocity from each side. And then we'll be able to separate the variables. So we have dv over v is going to be equal to minus k times dx. And then we integrate like this, right? And then if we integrate, we have on the left-hand side, we have the natural log of v. The absolute value is not really relevant in this case because v is positive. And this is equal to minus kx plus a constant, right? So we can use the initial conditions to find the constant of integration. So we know that at this point, right? So at this point, which is the point where x equals 0, the velocity is the initial value v0. So we've got ln of v0 is equal to minus k times 0 plus c, and that gives us c as natural log of v0. Right? And then we can rearrange this a bit to find x. So kx is going to be equal to c minus ln of v, which is, we found c as ln of v naught minus ln of v. And then we can use the log rules to figure out that this is just ln of the ratio, so v naught over v, right? So the distance is 1 over k ln v0 over v. So that's the distance with respect to velocity, not with respect to time, but with respect to velocity. Now, for the other part of the question, we're trying to find the time required to reduce the velocity to v0 by 2. Okay, so in that case, I'm gonna start with the acceleration formula again. So the acceleration is minus kv squared. And then we know the acceleration is dv over dt. And this is minus kv squared. Now, the question is specifically asking us about the relationship between velocity and time, right? Because it's asking find the time required to reduce the velocity to a half. So we want a relationship which has velocity and time, and that's basically it, right? And then we can solve this by separating the variables once again. So this is dv over v squared is equal to minus k dt. So this is dv, or let's write it as v to the minus 2 dv is equal to minus k dt, and then we can integrate both sides. We should do this here actually. Right, so the integral of v to the minus 2 is just v to the minus 1 over minus 1, and this is minus kt plus a constant. And once again, we can find what this constant of integration is. So at the initial time, when we start our stopwatch, the velocity v is v0. So we're going to use that, we're going to put it in. So minus 1 over v0 is going to be equal to c, because t is 0. So that's it. We found our constant of integration. So with this in mind, we can rearrange to find the time. So kt from this equation is equal to c plus 1 over v. Right? So I'm moving kt minus kt to the other side, and then this gives me 1 over v minus 1 over v0. So this is minus 1 over v0 plus 1 over v, which is, well, let's leave it like this for now, or just put the positive term first, like that. So t is 1 over k, and then 1 over v minus 1 over v0, and we can say that we can probably leave it like this, or we can bring it to the same common denominator, but in this case I'll just keep it as it is. So the question was, what's the time for the velocity to become half of its original value? So we can do that very easily. We can force the velocity to be half of its original value like this, and this gives us a time of 1 over k, and then 1 over v becomes 1 over this, which is 2 over v0, minus 1 over v0, which is 1 over k times 1 over v0. So time is 1 over k v0. So that's it. So we found the time, we found the distance with respect to velocity, and that's the end of the question.